This is an example problem where we find the specific heat of a metal. When we do these calorimetry problems, a large majority of what we spend our time doing is keeping ourselves organized. So in this problem, we're going to find our variables, find our numbers, and assign them to the appropriate variables for our formulas. Whenever we read these problems, we can kind of figure out which equation we're going to use based on the number of masses that are provided. So in this problem, as I'm reading, what is the specific heat? So there's my question word, specific heat, which is going to be letter C, and that's of our metal, with a mass of, so here's the mass of the metal that cools from, here's going to be our temperatures, when placed in 60 grams of water. So there's a second mass, which is going to tell me which equation I'm going to need to use, with an original temperature of 38 degrees C. So because it says two different substances, metal and then water, and also because it provides two masses, I know I'm going to be using mc delta T equals mc delta T. So I'll list these 6 variables and fill them in as I read. We know that we're looking for specific heat of the metal, so that's a question mark under metal, specific heat, which is C. M is the 48 grams. And then delta T, I need to do 260 minus 70. Since I'm subtracting those, I need to get 190.0 degrees C, because both of these go up to the tenths. For my water, it's 60 grams. Specific heat of water isn't provided in the problem, but you need to know that the specific heat of water is 1 calorie per gram degree C. We know it's going to be the number 1 because this is happening at 38. 38 is when water is still liquid. And then the change in temperature needs to be based off of how the water's temperature changes. Now, it doesn't say the final temperature of water, it just gives you the original temperature. But because the metal stopped cooling at 70, that means that the water stopped heating when it got to 70. Basically, what happens is the metal starts out hot and the water starts out cold, and they continue to increase and decrease temperatures respectively once they hit the same temperature, and that's at 70. So even though it doesn't provide water's final temperature, it's implied because the metal stops cooling once it gets to 70. So 70 minus 38 is 32 degrees Celsius. Because I have two substances, and again we can tell that also by the two masses, I'm going to use mc delta T equals mc delta T. So this is the plug-in to the equation phase of your work. You have the metal, then you have water. So left side I'm keeping metal. For simplicity's sake, I'm going to omit the units as I plug numbers in, but if you do include the units, all units will cross off except for the one that you need, and that unit will be calories per gram degree C. So without those units, it's 48 times C times 190, which is equal to 60 times 1 times 32. I need to solve for C, so I need to divide by 48 times 190. Do that on both sides. So C equals 60 times 1 times 32 all over, and this needs to be in parentheses, your denominator needs to be in parentheses, 48 times 190. Then I'm going to actually solve this. To solve this, you just plug this into your calculator. You're going to get an unrounded number that looks like 0.21052. Going back to sig figs, our masses both have 3. Our temperatures end up having 3, or at least this temperature does. So we can have 3 in our answer. Start at the first non-zero, 1, 2, 3. A 0 followed by a 5, 2. So this isn't a lone 5. We'll round up. So the specific heat of the metal is 0.211 calories per gram degree C. And again, all of these units would be left over if we actually included units in our work.